Okay, I think we are ready to proceed. So our next speaker is Fiona Seibold from EPFL, and she will tell us about integrable deformations of AdS3 strings. So please, Fiona.
Thank you very much, and thank you to the organizers for giving me the opportunity to speak at this wonderful conference. So in this talk, we will embark on an exploration of the landscape of integrable deformations of AdS3 strings. And let's start by giving you some motivation why constructing and studying this type of integrable deformation is interesting. One of the motivation comes from the celebrated AdS-CFT correspondence that we have already seen in previous talks, especially the duality between the type 2b superstring theory on AdS5 cross S5, which is dual to n equal 4 super-Young mills in flat dimension. And as was also already mentioned, it's some specific limit, namely the one where the strings are free, which corresponds equivalently to the planar limit in the gauge theory. These two sides of the duality actually become integrable models. So this is very interesting because the integrability machinery can then be applied in order to obtain exact results, so non-perturbative results, which allow to test the duality at any value of the 't Hooft coupling. And this then begs the question whether there are other theories, especially superstring theories, to which this powerful integrability techniques can be applied in order to learn new lessons about quantum gravity and holography. The answer, of course, is positive, and there are different ways to approach that question. So one direction is to look at integrable theories or holographic setups in the lower dimensions. So for instance, when the strings propagate on some background containing an AdS4 or AdS3 or AdS2 factor, and some of these string theories will still be integrable. And the lower you go in dimension, the less supersymmetries the theory has. So you will have much less supersymmetries than what you have, for instance, in AdS5 cross S5. And this generates new interesting physics that is good to understand. And the fact that you have integrability then allows to have some handle on these new properties. Another direction that can be followed is through the construction of integrable deformations. So instead of jumping in dimension, here you will construct something that is continuously deform some known integrable theories. So you start from some known integrable theories and then continuously deform it in such a way as to preserve the integrability of the model. And in this talk, I will merge these two types of directions, and I will consider integrable deformations of AdS3 strings. So I will go in lower in dimension, considering AdS3, and construct integrable deformations. Now, to restrict a bit the space of integrable deformations, that is pretty large, so we have seen in the previous talk these TT-bar deformations. I will be more interested in deformations that deform the space-time geometry in which the strings propagate, but there will be some connections, as I will highlight. And so this landscape is very broad, and in order to be able to restrict it a bit, I will consider supersymmetric integrable deformations. So the integrable deformations will break some of the supersymmetries, but some of them will be retained, and throughout this talk, this will actually be half of the symmetries will always be there, so half of the original theory here. And these results that will be presented are mainly based on work that I did with fantastic collaborators. So Ben Hoare, Anna Rettore, Alessandro Sfondrini, and Arkady Zeitlin, and the two last ones are in the room. The plan of the talk is as follows. I will just start with some very, very brief review on the status of integrable AdS3 strings. I think we will hear more about this program today and tomorrow. Then I will present what is perhaps the simplest type of integrable deformation that one can construct, namely TST transformations. I will then crank up a bit in difficulty and present trigonometric and elliptic deformations. So these are really newly constructed deformations that I want to present. And throughout this exploration, we will encounter the question, so how to test whether the theories that are constructed are actually integrable, and also both at the classical level and at the quantum level. And in order to answer that question, I will need to introduce the so-called worldsheet S matrix, and I will then see what this worldsheet S matrix, the form it takes for these different types of deformations. Finally, I will finish with some conclusions and give an outlook of open problems that still need to be addressed, and there are many. So let's start. Oops, sorry. Okay. Let's start with the AdS3 strings background. It will be the starting point of my integrable deformations. So there are three solutions to the type 2b supergravity equations of motion that have this AdS3 factor and that preserve 16 real supercharges. So these are the three backgrounds mentioned here: AdS3 S3T4, AdS3 S3K3, and AdS3 S3 S3 S1. There is a huge literature on this string theories. What will be interesting during the talk is that these theories have a superisometry algebra that have the symmetries factorized into two copies. So for instance, in the two first cases, these two theories present two copies of the PSU1,1/2 superalgebra, in which in each copy there will be 8 supercharges. And similarly for the third case, the geometry presents two copies of the D2-1 alpha superalgebra. So this parameter alpha in the D2-1 alpha, it controls the ratio between the three spheres that appear, the ratio of the radii of the 2 spheres that appear in the geometry. And by sending this parameter to 0 or 1, the S3, S1 geometry decompactifies into a T4. So there is a way to go from this geometry to this one. And similarly, it's also possible to do that at the level of the algebra. Another interesting factor is that these type of geometries have a lot of moduli that one can play with. In particular, they can be supported by different combination of fluxes. There is the pure NS geometry, there is the pure Raman, it can be supported by pure Raman fluxes, or also a mixture of both. So this is a difference with respect to, for instance, the AdS5 cross S5 superstring. And importantly for this talk, all of these three cases are integrable, at least in the limit of free strings. So this has been rigorously proven for classical integrability for AdS3 S3T4 and AdS3 S3 S3 S1, including by people at NORDITA. And it is believed that the integrability will also hold while when replacing the T4 with K3. So these are integrable string theories, and they will serve as my starting point in order to deform the theories. So let's start with the simplest type of deformation that I want to introduce, these TST transformations. So these TST transformations, you might already have encountered them, and they are interesting because they can be applied whenever the background geometry that you are investigating or working with presents two U1 isometries. And here I will assume that these two U1 isometries are realized as shifts into coordinates phi1 and phi2. So this TST transformation, as the name suggests, can be decomposed into 3 steps. The first step consists in doing a T-duality in one of these coordinates, phi1. It goes in some T-dual coordinate phi1 tilde, and at the level of supergravity, for instance, if starting from a type 2b background, this will map to a type 2a background. Then in this T-dual theory, you perform a shift involving the other coordinate phi2, a shift parameter beta, real, and this T-dual coordinate phi1 tilde, and then you T-dualize back in order to land again on a solution of the type 2b supergravity equations of motion. So some properties that make this type of deformation interesting. So first of all, it maps string backgrounds to string backgrounds. So you are always guaranteed while performing this type of transformation that you will land on a consistent string theory. And it's relatively easy to implement it at the level of the background because there are these rules, these Busher rules that really tell you how the metric, B field, and fluxes transform. Another interesting property of this type of transformation is that it often has a clear interpretation in the context of holography. So this is true, especially if the TST is realized not, of course, on the AdS factor to preserve conformality, but in the compact space. So for instance, I would say the canonical example of this is the duality between the Lunin-Maldacena background, which is a deformation of AdS5 cross S5, where the TST is performed along the two U1s inside the S5, which is dual to the Lie-Strasser deformation of n=4 super Young-Mills, which is still conformal, but preserves only n=1 supersymmetry. So these type of deformations have been, so for instance, for this example, they have been mostly looked at from the point of view of AdS5 cross S5. And there is some literature also for AdS3, but it's still in progress. And here I would like to show you some recent results. So I will start, the starting point will be where is the, okay. The starting point will be the AdS3, S3, S3, S1 background that I will focus on the pure Ramon case. In fact, throughout the talk, I will only consider the pure Ramon setup and construct deformation of this theory. So there are 4 different factors. AdS3, there are the 2 3 spheres, and there is the S1. And inside each factor, there are several U1s that one can play with. And they can be decomposed into the U1s that belong to the left D21 alpha and the U1 that belong to the right D21 alpha. And there is a similar decomposition for the 2 3 spheres. So the type of TST transformations that I want to construct. So first of all, I want to preserve the AdS3 background so that ultimately I want to be able to consider them in the context of holography. So I will not touch these 2 U1s. And then on top, I want to preserve half of the supersymmetries. So here I choose to only deform the right copy. So I will only consider these 3 U1s. So the U1 right inside the 2 3 sphere and the U1 of the S1 factor. So there are 3 U1s that I can play with in order to construct this TST transformation. So in principle, I could construct a 3-parameter deformation in that case. But this obscures a bit the geometry. And in order to convey the main message, I will focus on 1-parameter deformations. So I will consider the TST transformation in these 2 U1s and also the TST transformation in these 2 U1s. So let's start with the TST involving a U1 of the 3 sphere and the U1 of S1. In that case, the geometry, so again, it's the way you can implement this TST transformation is through these Boucher rules. And what to obtain is that the geometry, the sphere that is involved in the T-duality becomes squashed. So the metric takes the following form, where you have a base manifold that is S2, and then the fiber A, and then you have some squashing parameter delta in front of the fiber. And this squashing parameter is related to the TST transformation beta through this relation. So if you want to preserve reality, so beta is real, delta is between 0 and 1. This is why I call this a squashing. So this is for the metric, but of course one also needs to consider the whole geometry. So here I will give you also the dilaton of the fluxes. What is interesting is that the dilaton remains a constant. So we have seen in previous talks other cases where there is this type of warping factor, but this warping factor was depending on a dynamical coordinate. It wasn't a constant, and therefore there was also a non-trivial dilaton. But here this dilaton really remains constant. Another important feature is that while we started with pure Ramon background, this TST transformation generates an NS flux, and the 5-form flux is also turned on. So here delta equal to 1 corresponds to the undeformed theory, where the geometry is just supported by the 3-form flux, where here omega represents the volume form of the different factors. An interesting limit is to consider the strong deformation limit. So when the the parameter in the TST transformation goes to infinity, and in these parameters, this corresponds to sending this squashing parameter delta to 0. Now, in order to make sure that this limit is well defined and there is no the degeneracy in the metric, one also needs to do a rescaling of the coordinate in the fiber. But when doing that, the metric and the background fluxes remain finite, and there is a flat direction that appears, but all the fluxes remain turned on. And this, in fact, if you stare at it for a long time, or for a short time, this will give for you the AdS3, S3, S2, T2 background, which, as was shown in that paper, which actually gives the classification of backgrounds that are classically integrable and have an AdS3 factor. Well, this background was already found in that paper. Perhaps a slight remark is that here I wrote T2, but from this construction, of course, you cannot really distinguish between T2 and R2. So the conclusion is that starting from the AdS3, S3, S3, S1 background, doing this TST transformation represented by this line of series in this blue line, taking some limit, one can reach the AdS3, S3, S2, T2 background, which is another type of another classically integrable background, but with less symmetries. Here I put also an arrow going from that background to that one, but of course, because it involves this scaling limit, you cannot do that using in a straightforward way. Now, so let me just schematically tell you what happens when doing the TST transformation in the two U1s of each three spheres. In that case, you again get the squashing geometry, and the two three spheres are squashed with the same squashing parameter delta, and this allows you to construct a deformation, a family of series that then interpolates to AdS3, S2, T2, AdS3, S2, S2, T3, which is another known classically integrable background. You can also take this limit where alpha goes to 0 and 1 to land on the AdS3, S3, T4 background, and similarly to the TST there in order to land on yet another classically integrable background, AdS3, S2, T5. So what are some properties of these blue lines, so these interpolating backgrounds that are interesting? So first of all, they preserve the AdS3 factor, which makes them interesting to study in the context of holography. They also preserve, so throughout, for all this family of theories, they preserve the classical integrability of the theory. So in principle, all the integrability machinery can be applied to them. This is particularly interesting because these three theories have actually been much less understood from the point of view of integrability, and being able to construct integrable backgrounds where you can really follow what happens to the integrability techniques all the way down and take the limit, perhaps it will help us understand these backgrounds better. And throughout the flow, or throughout this deformation, you preserve 8 supersymmetries. And so these 8 supersymmetries come from the copy of PSU 1,1/2 or D21 alpha that remains undeformed while doing the transformation. So so this was one type of deformation that one can construct. Let me also just give you some comments. So first of all, here I only deformed the compact directions. It's also possible to deform the AdS3 factor because of the different signature. There will be the possibility to have time-like, space-like, and null deformations. Another comment is that by doing this deformation of AdS3, one can land on backgrounds containing an AdS2 geometry, which could also be interesting to be studied in the context of holography. Another comment is that these TST transformations are just special cases of a broader class of deformations that are called homogeneous Yang-Baxter deformations. This type of transformations, they really change the geometry and may break all of the supersymmetries, but what is important is that strings propagate, so strings with periodic boundary conditions propagating in these deformed backgrounds can equivalently be seen as strings propagating in the undeformed geometry but having twisted boundary conditions. So in some sense, this deformation changed the geometry globally, but not locally. So now I want to introduce other types of deformations that will really change the geometry locally as well. So these are these trigonometric and elliptic deformations. So the trigonometric deformation, it can be traced back to the work of Cherednik, who looked at the deformation of the principal chiral model on SU2, and this corresponds to having a string propagating on a 3-sphere. And this trigonometric deformation, again, gives this squash geometry of the 3-sphere. So here, I just wrote it in some other way that is more convenient later on when I will discuss also elliptic deformation, but this E1, E2, E3 are the undeformed film bind of the 3-sphere, and then there is the squashing parameter beta appearing here. However, contrary to the TST transformation, in that case, it is not supported by any B-field. So my geometries here will not have any NS flux, and this will make a big difference. One of the differences is that, so this geometry, so this principal chiral model has a left-acting SU2 and the right-acting SU2, similarly to what we have seen before, and this deformation breaks the right-acting SU2. However, there is actually a hidden symmetry, so this is a quantum group symmetry, and the way you can think of this quantum group symmetry is really, so this is really a deformation of the universal enveloping algebra, but naively you can just think of it as taking your generators of SU2, J3, J plus and minus, and then deform the commutator between the positive and negative root. Instead of giving a J3, this will give some Q deformation of J3. So this parameter Q is some real parameters that is related to the deformation parameter in the metric. So contrary to TST transformations, this really deforms the geometry locally. So you cannot really think of them as being strings with twisted boundary conditions. This trigonometric deformation or these quantum deformations, it is known how to generalize them to cosets. So for instance, to consider quantum deformation of S5 or AdS5, and also to supercosets, so how to deform superstrings. In particular, this can be used to construct deformations of AdS3, S3, T4 or AdS3, S3, S3, S1. The case of K3 is a bit more tricky. These deformations, they will preserve, again, H supersymmetries as long as the deformation is only done in one copy of the superisometry algebra. Now, a subtlety is that for TST transformation, it was always guaranteed that starting from a string background, you will land on a string background. Here, while doing this, so this deformation initially was really studied from the point of view of integrability, so it will preserve integrability, but the interpretation in string theory is a bit more tricky. And in fact, one can have different quantum deformations that are classified according to the Dinkin diagram of the superisometry algebra. So for instance, for PSU 1,1/2, there are 3 different Dinkin diagrams. So here the node with a cross represents a fermionic root, and the node here represents a bosonic simple root. There are some fermionic dualities that allow to go from one Dinkin diagram to the other. But what is interesting is that the interpretation of this deformation in the context of string theory is not equivalent for all Dinkin diagrams, and in fact only this fully fermionic Dinkin diagram leads to a supergravity background, so that you can interpret the deformation as some deformation of the string theory. So now elliptic deformations, they introduce an additional deformation parameter. So before, there was still a U1 rotating the 2 field bind E1 and E2, but here this is further broken down. And in fact, the whole right-acting symmetry is broken. Now, this type of deformation, so here written down for the 3-sphere, It can be generalized for non-compact groups, in particular to AdS3, but it's not known yet how to generalize them to coset models. So we don't know how to do an elliptic deformation of S5 or AdS5 cross S5, and we also don't know how to generalize them to supercosets, so how to do integrable deformation of superstrings in a systematic way. However, what we managed to do recently is to embed this deformed background, this elliptic deformation of AdS3, S3, and just having some flat T4 directions into supergravity, so into type 2b supergravity. So this turns out to be possible. And let me just sketch how the background looks like. So it has a trivial dilaton as for the TST transformation. So here for convenience, I will set it to 0. It doesn't have any NS flux. This is what I try to highlight, what is the difference with respect to the TST transformation. There is, again, the 3-form and the 5-form flux that are turned on, and these are actually given by linear combinations of 4 auxiliary self-dual and orthogonal 3 forms. So here, F3, 4, you recognize the volume form and AdS3 and S3, but the other 3, they really mix the AdS3 and the S3 sectors in a non-trivial way. And this X1, X2, X3, X4 are 4 vectors of 4 components that parameterize the deformation. Those are the deformation parameters in the Ramon-Ramon fluxes. The J2s are the self-dual orthogonal 2 forms on the torus. So, of course, there will be some constraints on these deformation parameters. So supergravity imposes constraints on the norm and the scalar product of these vectors of deformations. So this restricts them to just 10 parameters in the Ramon-Ramon fluxes, and also requiring that the background preserves A supersymmetries then also restricts these further. So this is actually equivalent to the statement that the vectors of parameters lie in a 2-plane. And we also checked that the killing vectors and the killing spinors of this geometry generate the PSU1, one copy of the PSU1,1/2 superalgebra. So the bosonic model was constructed using this Cherednik elliptic deformation, and it's known that this preserves the integrability of the model. And we also managed to embed this integrable bosonic theory into supergravity, but what about the supersymmetry? So is it an integrable theory, what we just constructed? And in order to address that question, I need to introduce for you the concept of worldsheet S matrix, which will really allow us to test the integrability of the model. So this is a picture of the integrability program applied to the string sigma model. So the string sigma model has a lot of redundancies. So there is some reparametrization invariance. There is also some symmetry, kappa symmetry for the fermions. And the first step is to gauge these symmetries away. And this is done through what is called the Lycon gauge fixing that we also have briefly encountered in the previous talk. This then defines a theory on the cylinder. So here I consider closed strings. So this is the worldsheet of the closed strings. And then the additional step consists in taking the decompactification limit, where now this decompactifies into the plane. On that plane, you have a well-defined two-dimensional quantum field theory, for which you can define asymptotic states. The S matrix can be computed. And integrability then imposes restrictions on this S matrix that we have also seen in the previous talk. In particular, there cannot be any particle production, and a n-body scattering event factorizes into two-body scattering processes. And this imposes some constraints on the two-body S matrix, which is the celebrated Yang-Baxter equation that was also mentioned. So in order to test whether the model is integrable, one way to do that is to follow this route, compute the S matrix, and check that the Yang-Baxter equation is indeed satisfied. So I will not go through the details of this Lycon gauge fixing. However, I will mention that for the AdS3 S3 T4 case, doing this procedure then gives you a non-relativistic theory for 4 massive bosons, 4 massive fermions, and also 4 massless bosons and 4 massless fermions that come from the T4 directions. The S matrix, of course, you can compute it using perturbative calculations, but really the power of integrability is that in that case, you can bootstrap it using symmetries. So here, I wrote down the bootstrap equation for the S matrix. And again, there are some caveats. So this only fixes the S matrix up to dressing factors that still need to be fixed using more physical input. And this program has been followed with great success for the undeformed AdS3, S3, T4, and also AdS3, S3, S3, S1 case. Now, what happens for the deformed theories? So one first comment is that in these deformed theories, sometimes you break the symmetries that are usually used for the Lycon gauge fixing. So one needs to consider alternative Lycon gauge fixings, and different choices of these Lycon coordinates that enter the Lycon gauge fixing, they actually lead at the level of the Lycon gauge fix theory to TT bar deformation that we have just seen, but also more general current deformations. Especially, and a corollary of that, if you want, is that if you do a TST transformation in the 2 directions that are used for the Lycon gauge fixing, this actually corresponds to performing a TT bar deformation at the level of the Lycon gauge fix theory. So this is when the TST is performed in these coordinates that are used for the Lycon gauge fixing, but you can also do the TST just in the transverse coordinates that are not affected by this Lycon gauge fixing. And in that case, the S matrix gets dressed by a Drinfeld twist. And this Drinfeld twist satisfies some co-cycle condition, which really ensures that if you start from an S matrix that satisfies the Yang-Baxter equation, this dressed S matrix again satisfies the Yang-Baxter equation. So integrability is preserved, as it should. For trigonometric deformation, this is not possible, so you cannot do this twisting, again, because the geometry is changed locally, but you can use this hidden quantum group symmetry in order to, again, bootstrap the S matrix. So remarkably, this quantum group symmetry is still powerful enough in order to bootstrap the S matrix, and this has also been done for AdS3, S3, T4. However, for elliptic deformations, the symmetries and the exact S matrix are not yet known. So we don't know what the symmetries are. We don't know what the generalization of this quantum group symmetry, which would be some type of elliptic symmetry, would be. So, however, we can make progress by just considering perturbative calculations, just as in standard quantum field theory. And we will restrict to the massive sector because I told you there are some massless bosons, massless fermions that appear, and these, in perturbation theory, they are problematic because they involve some IR divergences. So here, in order to be safe, we will just focus on the massive sector. So the Lycon gauge fixed theory can be expanded in inverse of the string tension, and similarly, then the S matrix has some is the identity plus the first interactions plus high loop corrections. So what we did is to compute this 3-level S matrix using the background that we suggested, and we found that it satisfies the classical Yang-Baxter equation, which is a strong indication that the model is actually integrable. So that's very good news. The S matrix that we find has a completely new form with respect to undeformed AdS3, S3, T4. It's reminiscent of an 8-vertex model, but it falls outside of the different classifications that have been done so far. In a limit, it also goes to the 3-level S matrix on AdS2 cross S2, so it provides some interpolating S matrix, which is again interesting because these geometries are also not well understood from the point of view of integrability. So let me now come to the conclusions and an outlook. So conclusions is that there is a very rich space of integrable deformations of AdS3 strings. Some of these deformations preserve 8 supersymmetries. Some interpolate between known integrable backgrounds. We also constructed a new type of elliptic deformation of the AdS3, S3, T4 superstring, and we checked that the tree-level S matrix is compatible with integrability. It presents some new interesting features, so it would be very interesting to build on that work and to actually try to find some exact S matrix that represents this type of integrable scattering. So what are some open questions? So as I just said, so it would be very interesting to find the symmetries in this elliptic deformation to be able to construct an exact S matrix. It would also be interesting to understand the relation between these two other types of S matrices of 8 vertex type that were constructed by just bootstrapping the Yang-Baxter equation. Because I said it falls outside of this category, this classification, so whether this classification can be generalized. What is the relation to other types of integrable interpolating S matrices that have been recently proposed? Also here I really told you how to obtain the S matrix for these integrable, these deformed theories, but obtaining the S matrix is really the first starting point to apply the integrability program. So we still need to understand the beta ansatz, the thermodynamic beta ansatz, or even find a quantum spectral curve for this deformed AdS3. So this is something that even is under progress for the undeformed case. So first one is to fix that. Another question is that there, in the literature, one can find many other families of supersymmetric backgrounds that have this warped AdS3 or S3 geometry. And so what is the status of integrability in these theories? Are they somehow related to the ones that are constructed through TST transformation or these trigonometric deformations? That would be interesting. Another one is how to lift this type of deformation to the brane setup. And of course, the bigger question is how to interpret the type of deformations in the context of holography. Thank you very much for the attention.
Thank you very much for the nice talk. Other questions?
Thank you. Thanks for the talk. Could you comment, please, a bit more on integrable deformations for warped AdS cross-S geometries and potentially the holographic interpretation?
Okay, so in the literature, using compactifications, there have been geometries that were proposed that also have this warped AdS3 geometry of also null or time-like or space-like warping, and also deformed S3 geometry, and they also obtained some fluxes. But this was obtained from, I would say, a supergravity perspective, and whether these models are integrable or not, this has not been explored. So this is what I was meaning here in terms of what would be interesting. The other point about the interpretation in holography, so I mentioned that for AdS5 cross S5, at least in one specific case, we have a good handle on what these TST transformations, for instance, do at the level of the duality. We know exactly what the dual CFT is. So what happens for these deformed theories? This is what this open question is. So in the case of AdS5 cross S5, where well, first of all, in the undeformed theory, the dual is known. It's n equal 4 Young-Mills. There has been some progress for these like homogeneous Yang-Baxter deformation or TST transformations, and this correspond to more general non-commutative geometry. However, for AdS3, even the undeformed case is still explored. Especially what happens in the case of Ramon fluxes, which is really the setup that I chose in that talk. And in that case, yeah, very little is known about the interpretation in holography.
And what do you expect what do you expect the holographic interpretation to be in the warped case in this?
Okay, so you probably mean in the warped AdS3 case, right? Yeah, so this will, so in that case, you will no longer have a CFT, or at least you will no longer have a CFT2, but because you still preserve one copy of the SL2R, in some sense, there is a one-dimensional CFT sitting in there, so there will be also some interesting results in that sense.
Thank you very much.
Do you know what happens with Drinfield's twist in this limit delta goes to 0?
In which twist?
Drinfield.
In the Drinfeld twist, when delta
In
goes...
TST deformed case, when you take delta to 0, do you know what happens with the Drinfeld twist?
No, I don't know, because there is a whole chain of calculations that one would need to do. So first you would need to understand the Drinfeld twist starting for this AdS3, S3, S3, S1, and then take the limit. So I don't know, but it should, it can be worked out.
Thanks for the nice talk. In AdS3 backgrounds, we expect not only the PSU or D algebras, but a full superconformal algebra, right? Either because logic being either there's a CFT dual, CFT2 dual, or because of the Brown NO construction in supergraph. Is any of this infinite dimensional algebra seen in these constructions? And I mean, so in NSNS background, for instance, this Givon, Kutasov, Seiberg, that constructed these charges. What happens to that under these transformations? Do they stay invariant, or do they transform into a new set of charges?
So I am not sure, but of course, because these theories are integrable, they also have this hidden Yang-Yang symmetry, so there perhaps is some relation to that. And this Yang-Yang symmetry, in the case of the trigonometric deformation, this is really what becomes the affine quantum group. So this is, you can also trace back in these type of theories what happens to these higher charges.
And how does it transform under your TST or these transforms you're doing?
So for the TST, what happens is that there is you get a twisted algebra in some sense. But yeah, I cannot answer specifically because I'm not very familiar, but I can try to make the link with what happens in integrability.
Talk more later. Thanks.
If there are no more questions, then let's thank the speaker again.